All right, so what we've done there is we've taken that shape, we've broken it up into two pieces, a rectangle and a triangle. So the rectangle, as shown on the left there, has a height of 30, and the triangle is the difference between that rectangle height of 30 and the total height of 78, so that gets you 48. So what you would do then would be to replace each one of those shapes with, you find the area under the shape, one for the rectangle, the other for the triangle, and then place the loads at the centroid of the shape. So what we've got there is we've got, for instance, for the rectangle, so the force for the rectangle, what that is 30 kilonewtons per meter. And then that base is 6 meters. So when you multiply that out, you'll get 180 kilonewtons. Okay, so that's going to go right there. And then that will be located half of the 6 over, so that'll be 3 meters over. So 6 over 2 gets you 3 meters. That's where the centroid of a rectangle's at. Okay. Now you're going to want to do the same thing for the triangle and get the load associated with it. Okay. And you can just run those numbers, and 144, I think, 4 meters. Okay. And then you just make a resultant problem out of it. So when you have these distributed loads, the approach on this is just to first break them down, or find their area, I guess would be a better way to put it. And that's the amount of the load, and then put that at the centroid of the figure, which is the distance that those forces are from the whatever point you're referencing to. In this case, it's point A. Once you've got that, you can add the forces up and get the resultant force, and then do moments about whatever point you like and get the resultant moment. Y'all okay with that? Yeah. Yeah, the 3.4 meters is the same process that we're using back here. It's what you're doing there is you're saying, where should I put the force such that I can get the offset distance that would get me the moment, okay? So for instance, on this one, you've got a total moment of 27.1 kilonewton meters. Now what you know is there's this force, this resultant force is causing that. Now if you look at where that thing's placed, it's not going to be the total force, it's going to be the y component only, because the x component, if you just slide the force along that beam horizontally, the x component will not cause a moment about A. All right? So what we're doing here is we're taking the force and we're looking at each component, and we're going to realize when we do that that the x component goes right through A and causes no moment about A. So it's going to be the y component that causes the moment. And what that is, as we slide it over there to the left, or right, excuse me, we're going to get 7.89 kilonewtons. That's the y component. And that'll be times the unknown distance. And then you just solve for the unknown distance, and that comes out to be 3.43. So that's the distance over that you would place the force such that it creates the moment of 27.1.
So in this problem, you have found you need to find the distance before.
No, you find the moment first and then back into the distance on the one we're working on now. It's always the same process on these resultant problems. Okay? So just find the moment that's caused by that distributed load, and then based on that, you can come up with the distance by knowing the force. So you good on that? You got questions or? Okay. Or,
For a triangle, how do you find the what's that called, the centroid?
yeah.
It's 2/3.
2/3 of the distance from the vertex.
2/3.
Yeah, the centroid's located 1/3 of the distance over from the right angle and 2/3 of the distance over from the vertex. So the centroid's right there. That's d over 3, or whatever you want to call the variable, and that's 2d over 3, always. So you just find the moment caused by those two forces, and then find the force, divide them out, you get the distance. Other questions on that? Okay. Okay, I'd also like to have you verify that that force diagram is correct, okay? So the way you're going to do that is you're going to look at how much of that floor slab, the concrete, and then the sand above it is sitting on a beam. And it looks like the beams are 2 meters on center, so each beam is going to support 2 meters of slab and sand, okay? So basically what I mean by that is that total slab is 4 meters, but there's 2 beams. So each beam then will support half of 2 meters. It's or half of 4 meters. It's 2 meters across. Okay. Now the concrete, if you look at that, weighs 24 kilonewtons per cubic meter. So that's 24 kilonewtons per meter cubed. Now what you've got there is you got a 2 meter width. All right, and actually, why don't we put the height into that first? I'm sorry, let's do that. 0.625 meters. Okay, now what that's going to get you then is the weight per unit area pushing down from the slab, from that concrete. So we're just looking at the concrete here. And what we're finding is the weight per square meter of the concrete is what we're finding there, because we're taking the unit weight of concrete times the thickness, the 0.625 meters over here. So that gets you how much a square meter of concrete weighs. Okay. Now we also know that each beam supports a 2 meter width of concrete. So if you take the weight per square meter and multiply it by the standard width of that slab that one beam supports, that will get you the kilonewtons per meter of length of beam. Okay, so if you multiply that through, what you get is 30 kilonewtons per meter of beam. And see, that's the value right there. So I just want you to verify where these numbers come from. Okay. So concrete's 24 kilonewtons per cubic meter. This particular concrete slab here that we're working with is 0.625 meters thick. So if you multiply that by the unit weight of concrete, you're going to get the force per square meter. And then the width of the slab that sits on a given beam is 2 meters. Multiply that through, you'll get 30 kilonewtons per meter of length of beam. So that's where that lower portion of the diagram comes from. Okay. So we got this, we just did that. Okay, now for the sand, there's no sand at A. So at A it's 0, but then you're going to want to verify that that distance there is good for the sand. Call that point B. And just verify that point B has that height of sand, and then go ahead and calculate the load per unit length of the sand on the right side. And this, we did this yesterday too. You know, you start off with a unit weight of the material, multiply it by a depth. That gets you the weight per square unit. Multiply that by the width that's being supported, and that'll get you the weight per unit of length along the beam in this case. We did the same thing for water yesterday.
You do the highest depth, or you just multiply by the depth?
Yes.
So would that just be like 1.2 meters, or?
Yeah.
So you do the highest.
Well, that's the depth that we.
Oh, right. We're trying to find.
Yeah, because we know it's a straight line between the line A and B. Draw, you know, you can draw that straight line between. You got the diagram. You good with that? So, you know, often in a statics book, you get the diagram down below. I just want you to walk through the process of getting from the diagram above down to the diagram below. So, you know, if you're designing this situation here where you got beams 2 meters on center supporting the concrete and the sand, how do you generate the diagram below? That's what I'm asking you. Okay. Where does that come from? So you just got to figure out what's going on in B. Okay. We're good with that? All right, then we got this thing here. Now this one's, we just want to find the resultant at A that occurs when you have this loading diagram here. So I would do this one kind of piece by piece and kind of work my way on down through it. What you want to find the resultant at A. So to accomplish that, what I would do is I would break it up into pieces. So what you've got there are 2 rectangles and a triangle that you're going to break up. Like so. So you're going to want to find the centroids of these things. And then once you've got those, you're going to want to find the distance from the point A to those centroids. Okay. Now the first point we'll reference here will be this break point here where it says 740 newtons per meter. That's the most basic distance that you can dimension. So we'll probably start with that, okay? So we're going to use something like that. So what we got there, for instance, is we have dimensions down here. So we're going to have, for that rectangle, we're going to have half of 1.2, and that'll be 0.6 meters. And then you'll have a third of 1.2, and that'll be 0.4 meters. So 1.2 over 2 is 0.6 meters. 1.2 over 3 is 0.4 meters. Okay. So what I'm doing there, I'm measuring from the natural break point there between all those figures, that edge there, to the centroids. Okay. And from there, what you would do would be to dimension these shapes and start to figure out their areas, I think. So that'd be 740 over there. Be 210 right there. And then what, 740 minus 210? 530, I think. Y'all okay with getting that 530? Just 710, which is the total height, 740, which is the total height minus the 210. Okay. So then, once I've got that, what I would do then would be to find the areas of the shapes. So we good on those distances? And the heights? Okay. Okay. All right, and then for instance, you've got 210 newtons per meter times 1.2 meters. So what you would get for that would be 252 newtons. Okay, so that's this value right here. It's 252 newtons. Now what you want to know is how far it is from A, okay, because we want to know the resultant at A. So what you would do there would be to dimension from here on out. So that would be an X dimension measured from A. So what you're going to have then is you're going to take the 0.6, but you're going to have to add in 0.2 meters, okay? Because that force is 0.8 meters from A. So that's a Newton measurement there. Okay. And that's measured from A. Okay. So you get those initial measurements in blue on the top there, the 0.4, the 0.6, and then the what, 0.55 I think it is. Those are measured from that boundary between the figures, because that's kind of the natural place to measure those. But we're taking the resultant at A, so we basically have to shift all those measurements by 0.2 meters over to get to A from that boundary. That's the idea. Okay. So what you would do with this thing is sum the forces. And of course there'll be 3 of them. And when you do that, you should get negative 1384. Just add the 3 forces together. And then you'll sub moments about A. And again, you'll have 3 moments about A. You'll have, for instance, that 252 newtons. Times 0.8 meters. You'll have another one to add in, and then you'll have a last one to subtract. And just total all those together. And what you get will be positive 107.5. So that's 107.5 Newton meters. Y'all okay with that? So what you're going to do is add the 3 forces together and then combine the 3 moments together. 2 of them are positive, 1 of them is negative. Okay. just remember to include that 0.2 offset in there, because those measurements to the centroids are taken from this edge right here in blue, right there, this boundary, but you're taking moments about A, so that's 0.2 meters away. So you got to adjust all those dimensions, either add or subtract 0.2 meters. Okay. Right. Questions on that? We're good? Yeah. All right, so that's just due tomorrow. Okay, so the next thing that we'll look at here, kind of going on down the road, is free body diagrams. And this is what we're working towards is solving out equilibrium problems. Free body diagrams is kind of the next step towards doing that. So we want to be sure that we can do this. So what we're going to do, we're going to drop sketches of different things we might encounter and show the forces and moments that are associated with them. All right, so what we're going to do, and we've done this just a little bit before. We didn't do it in any great detail, but we did a little bit of it. We went ahead and we found free body diagrams of just little points, basically. What we're going to do now is find free body diagrams for a little bit more complicated objects. So this is on page 360. So we're on page 360. So what we're going to do first is figure out what we want the object, which is called a body, to be, draw a boundary around it, and then draw on the forces acting on it. Forces are either caused by direct physical contact, or they can be caused by force fields like gravity. All right, now we've got two different types of forces. We've got actions, which are the applied forces, which we've been looking at here so far, but we also have things that support the object, usually by physical contact, and they're called reactions. The forces at these supports are called reactions. Once you know the actions and the reactions, you know all the forces acting on the object. Once you know that, you can start to work to design it so it can withstand those forces. Okay. So generally speaking, what you do is you look at a support, and if you want to find the reaction caused by the support, look at the motions that the support prevents. Reaction forces and moments are required to prevent motion. So if a support prevents motion in the x direction, there has to be an x reaction to do that, some sort of force in the x direction to do that. Now when you assume the directions of forces, you can assume them usually either way, and if you happen to guess wrong, you'll just get a negative sign for your answer, which is no big deal. So if you assume one of these reactions is upright and it's actually down left, you'll just get a negative answer. No big deal. Okay? Don't worry about that. You can fix it pretty easily. Okay? So what we're going to do is we're going to look at these supports and see what types of motion they prevent. Okay? We've looked at this one already. This is a cable. Okay, now the force in a cable goes right through the cable. All right? So the direction of the cable is also the direction of the force. Cables pull only, so they're always in tension. So the force in a cable acts in the direction of the cable. Cables can only pull, they can't push, so they have to pull. So if I want to know how that cable affects this linkage, I draw my boundary around the linkage. In so doing, I cut through the cable. when I cut through it, it becomes a force, and that can pull only on that linkage. So that would pull up left at that angle shown by the cable. Okay. There's a cable. Okay. If you look around, you'll see lots of these here and there. So there's a crane of some type. These are used a fair amount to be holding up telephone poles and stuff like that. So if I were working on that, each one of these cables then would become a force that pulls on the pole. So that's what you'd be dealing with if you were designing this pole and all these things pulling on it. They'd all turn into forces, okay, that pull. Like I say, you see these around a lot. Here, those are cables, so that's basically what they act like. They might be more I think they're cables. They're going to pull back on that structure there and hold it up, to help hold it up anyway. Okay. They might have had that sign put up first, maybe it started to sag a little bit, so they put some cables on there where they could pull it back towards the building. Okay, the next thing is a linkage. Okay, I'm on page 360. Now, a linkage is similar to a cable. The force goes between the two pins. So a linkage usually has two pins on it, usually with a narrow piece of metal between them. Okay, now if there's only two of these pins, it's a link. And if it only has two pins, the force goes between the two pins. So you just draw the line of action of the force runs from one pin to the other. It might push, it might pull. You don't really know. Okay, so the force in a link acts from one pin to the other. The force can push or pull. Linkages have those two connections. And so they're called two force members because there's only a force at each pin. That's something that we'll deal with later when we deal with trusses. We'll look at these things in a lot of more detail. But for now, just understand that the force goes from one pin to the other, okay? Okay. There's a link right there. Okay, there's a number of other reactions that are kind of similar. Commonly, they're rollers. It could be a single roller or a multiple roller. They also can have rocker, which is just an angled portion cut out of a roller, or a smooth surface, which is assumed to be frictionless. These things all act the same. And the way they act is the reaction is always normal or perpendicular to the surface. Okay? So the roller allows them to move freely parallel to the surface. So the force is always normal to the surface they act on. So the force of a rocker, roller, and smooth surface is normal to the surface on which the roller rests. Okay? And the reason is they're free to roll or slide or do whatever they're going to do. There's no resistance to them moving parallel to the surface. It's all perpendicular to it, okay? So if that's a smooth surface, or maybe more correctly, if you assume it to be a smooth surface, you would assume then that the force is perpendicular to the surface, just pushes up on that handle there, okay? A caster is a roller. There's a multiple roller. So the force would be normal to the surface on each one of the rollers. If you put that on an incline, the force will be normal to the surface again like so. You can also go 3D on these. Oh, what's that? What type of connection do we got there? You seen these? These are really old draper rods. They don't much make them this way anymore. They're kind of a pain, but those things will slide this way. And they're also free to rotate. So they'll rotate like that if you like. And they're held in that channel. What do you got there? What would you call it? It's a roller, yeah. It's a roller basically. I guess it is kind of a link hanging off of that, yeah. So that thing's a roller in that channel. It's not allowed to move up or down, but it's free to move left or right. There's a 3D roller that would roll any direction. All right. So we got those 4 due tomorrow, and then we'll carry on with this stuff tomorrow too.